want to talk about the idea of dissolving as a reversible process. So we've talked a lot about solubility in the past. We've learned the solubility rules. We've predicted when precipitates will form based on those rules, but we haven't actually talked about solubility in the context of equilibrium, even though we know that based on our discussions that dissolving is reversible. Things can dissolve and things can precipitate. That relationship goes both ways between a solid substance and an aqueous substance. In the forward direction, we call this dissolving. In the reverse direction, we call it precipitation. So we've experienced both directions. We've talked about both directions, but we haven't actually applied our understanding of equilibrium to the concept of solubility and stuff dissolving. So the dissolving process, like any other equilibrium, can be described by an equilibrium constant. So this equilibrium constant is known as the solubility product constant. And that makes it sound like it's something new and different, but it's really not. This functions exactly like any other K, but whenever we are referring to a dissolving process, the K is just referred to as KSP, or the solubility product constant. So it's no different than any other K, than any other equilibrium constant. It's just referring to a specific type of reaction. So if we have some ionic compound in its solid state, this would be in equilibrium with its aqueous ions, is the reaction that we are talking about here, where the forward is that substance dissolving and the reverse is the precipitation. So the KSP expression for this would just be the product of the ion concentrations, which is where the name solubility product comes from, is it's the maximum concentration of the ions multiplied together, raised to any exponents as necessary. So we have this new idea of KSP, the solubility product constant, that is a little bit different from what we have previously referred to as the solubility of a substance. So solubility, sometimes also referred to as the molar solubility, is the maximum concentration of a saturated solution. It's the maximum concentration of something in solution, aka the concentration of a saturated solution. Oops, didn't mean to zoom there. So saturated is the maximum amount of stuff we can have dissolved. So a saturated solution is one that is at equilibrium. So in a saturated solution, the solid and the aqueous ions are in equilibrium with one another. So the dissolving process, that reaction that we've been talking about, has reached equilibrium. So the value of KSP actually gives us a general idea of the solubility of a substance. It doesn't tell you exactly what the solubility is, more on that. Value of, KSP. But if KSP is really, really big or really, really small, that tells us something important. So the value of KSP gives us a general idea of the solubility of a substance. So a big KSP, if we think about how K's work, we look at our KSP expression back up here. A big value of KSP means that the value of our ion concentrations must also be pretty large. So that means there's a lot of stuff dissolved in our solution. So if we have a large KSP, that is something that we generally consider soluble. So anything that the solubility rules tell you is soluble in water would have a fairly large value for KSP, generally something larger than 1. Anything with a small KSP would be the things that we generally consider insoluble. So we can get this kind of general vague idea of, is it going to dissolve, is it not going to dissolve, by looking at KSP. But one thing we can't do is use the value of KSP to directly compare two substances. So KSP is nice as a quick assessment of, is it soluble or is it not? But if we're looking to compare substance A to substance B, we can't just look at the KSP values most of the time. So we cannot use the value of KSP to directly compare two substances. Two substances solubility. And the reason for that is that the relationship between solubility and KSP varies. So we said the solubility was the molarity of a saturated solution. How that's related to KSP depends upon the equilibrium expression. So the mathematical relationship between solubility and KSP varies according to the equilibrium expression. So it's not always going to be the same for two different substances. So looking at KSP doesn't necessarily tell you what the solubility is mathematically in the same way. So we'll look at an example of this in just a second. I think it'll make more sense then. So in order to actually compare two things directly, we need to actually calculate the value of the solubility. And we can do that using an ice table. And in our ice table, our solubility is going to be x. So we always use plus x minus x to indicate the change in our concentrations as our system approaches equilibrium. And so we'll essentially just be solving for x in order to find the solubility of our substance. So if we look at an example here, if we want to determine which of these two hypothetical substances is more soluble if given their KSP values. So let's say we have AZ, which has a KSP value of 4.0 times 10 to the minus 10th, and we have BZ2, which has a KSP of 2.4 times 10 to the minus 11th. So they both have very small KSP values, so they're both not really soluble in water. Looking at these two, the KSP for AZ is larger than that of BZ2. So the easy trap that most people fall into is, oh, KSP is bigger, it must be more soluble, right? But not necessarily. So we're going to go through and actually calculate the solubility, calculate the concentration of a saturated solution for both of these substances. Remember that we can't just compare KSPs. we need to actually calculate the solubility. Which is going to be X in our ice table. So, what exactly are we doing in terms of setting up an ice table here? So in order to have an ice table, we need to have a reaction. KSP is always the solid substance forming its aqueous ions, is the reaction that we're talking about. So we're going to need to do this for both of our substances. We've got, oops, thinks my A is a triangle. Excellent. We've got AZ in equilibrium with A is our cation, Z is our anion. It doesn't actually matter what the charges are, but they would be charged particles. So setting up our ice table, ICE. AZ is a solid, so we're just going to completely ignore that as usual. Now what our I row represents here is often a little bit confusing for people. So I, we know, stands for, come on, there we go. I stands for initial in our ice table. So we want to think about what is our initial state in this particular case. So the initial state means before any reaction has happened. So that means when we have just AZ and no ions have formed yet. We have just reactant and no product before anything dissolves in water. So in the case of solubility equilibria, the initial state always represents the pure solvent, which in this case is water. So in pure water, we have no A ions, we have no Z ions. We don't know what they are, but they're not in water. So in most cases, your pure solvent is going to be water. Not always, we'll deal with that in the next lesson. But if you're just dissolving it in water, your initial ion concentrations are typically going to be 0. You don't have any stuff already dissolved, there's nothing in there. So then as we move towards equilibrium, since we started with nothing, we know our concentrations must increase, but we don't know by how much. So we'll leave them in terms of X. Our stoichiometry here is 1 to 1. So we'll have plus XA plus XZ. So at equilibrium, we'll have an X molar concentration of A ions and an X molar concentration of Z ions. So now we can actually solve for X, and we'll do that using our equilibrium expression. So the equilibrium expression for this, concentration of products over reactants raised to the power of their coefficients, ignoring liquids and solids. Our products are A plus and Z minus, each with a coefficient of 1, so an exponent of 1, and then our only reactant is a solid. So we're done. That's our KSP expression. We're given a value for KSP of 4 times 10 to the minus 10th. And from our ice table, at equilibrium, the concentration of A is X, the concentration of Z is also X. So to solve for X, we'll just need to take the square root of both sides, which will be 2 times 10 to the minus 10th. And that is a concentration. That will be a molarity. So this is the solubility, or the molar solubility of this mystery substance AX. So that means a saturated solution of this compound would have 2.0 times 10 to the negative 10th moles of the stuff actually dissolved for every liter of solution. So this is what we're looking to compare if you're asked which of these is more soluble, is to actually look at the solubility. So this is our solubility for AX. We're going to want to go through the same process, or sorry, AZ. We're going to want to go through the same process for BZ2 to figure out the solubility for that. So why don't you pause the video here and try to do that for that other substance. So you'll need to write out the dissolving reaction, set up your ice table, write your KSP expression, and solve for x. So now let's work through this together. So doing exactly the same thing that we did above, actually let's do it in a different color. So for BZ2, our dissolving expression will be similar, except that we have to remember that 2 subscript is going to become a coefficient. So we have B as our cation, and we're going to get 2 Z's in solution as our anion. So setting up our ice table here, BZ2 is a solid, so we can ignore that. Our initial state is pure water, so we're going to have concentrations of 0 to start for both of our ions, which means that our change must be positive, since we can't take away something that isn't there, but we don't know how much it's going to change by. So the concentration of B ions will increase by X, but because of the stoichiometry of this reaction, the concentration of Z is going to increase by 2X. So at equilibrium, we'll have X molar concentration of B and 2X molar concentration of Z. Whew. So now writing the equilibrium expression, KSP is going to be equal to the concentration of B ions times the concentration of Z squared, because of that coefficient of 2 again. So now we can plug in everything we know. The value we were given for KSP is 2.4 times 10 to the minus 11th. From our ice table, the concentration of B is X, the concentration of Z is 2X, and that gets squared. So if we simplify this, this becomes 4x cubed. Remember that we are squaring both the 2 and the x here, so this portion becomes 2x squared, and then we're multiplying by x again to get us to a grand total of 4x cubed. So once we solve that for x, we find a value of 1.8 times 10 to the negative 4th molar concentration. So this is the concentration in a saturated solution, or the molar solubility of BZ2. I just realized that I wrote X up there when I meant Z. So now we have the molar solubility for both of our substances here, for AZ up top and BZ2 down the bottom, and we can see that the molar solubility of BZ2 is much higher. It is 6 orders of magnitude larger than that of AZ. So this one is a whole lot more soluble, despite the fact that it has a smaller KSP value. It actually has a larger solubility because the mathematical relationship isn't the same. So if we look at our KSP expressions here, so I'm just going to simplify this down to x squared, since that's what it works out to be. If we compare the relationship between x and KSP, which is the step before our final answer, we can see that it's not the same. So x is our solubility. For our first substance, the solubility squared is related to KSP. For the second substance, we're relating to the solubility cubed times 4 is equal to the KSP. So the difference in relationship between KSP and solubility means that we have to actually do all of this extra work in order to be able to determine which of these two substances is more soluble. If you have a situation where the two expressions are the same in terms of x, then you can compare KSPs, because if KSP is larger, x is going to be larger if KSP is x squared in both cases, for instance. But if you have different expressions, as is the case here, then you have to actually calculate out the value of the solubility.